This is tutorial 6 and problem 10.8. So the problem goes as follows. As shown, the water, which is at 15 degrees C, is flowing from a tank through a tube and then discharging to ambient. The tube has an internal diameter of 8 millimeters and a length of 6 meters, and the resistance coefficient is F equals 0.015. The water level is 3 meters above the outlet. Find the exit velocity in meters per second. Find the discharge in liters per second, and sketch HGL and EGL. Assume that the only head loss occurs in the tube. Alright, so in other words, we told to ignore the head loss at entrance to the pipe. So we are going to calculate what the exit velocity and the discharge is. So what I've done so far is I've written down all the information given to us: the tube inside diameter, the tube length, which is 6 meters, the friction coefficient, that's between the pipe and the water flowing in it, 0.015, and the height, total height of the water level above the exit is 3 meters. Looking up the water properties on table A5, we get a rho value, density of water is 999 kilograms per cubic meter, and the kinematic viscosity 1.14 times 10 to the minus 6 cubic meters per second. So, as we know, for these problems we use the Bernoulli equation, which is an equation showing the energy in various forms from one point to the other one. So we can apply Bernoulli between 2 points, which is the water surface and the outlet. So let's write down that energy equation for this particular problem. We've got P1 divided by gamma, that's pressure at point 1, which is the water level. And then we've got alpha 1 V1 squared over 2G, which is our velocity term. We've got Z1, which is a height, plus HP, which is our pressure head. At point 2, we've got very similar, it's P2 over gamma, and then that's alpha 2 V2 squared over 2G, plus Z2 plus HT plus HL. So HL would be the head loss in the pipeline. So let's analyze these terms. The pressure at those 2 points, at the water surface level and at the exit of the pipe, is atmospheric, so we can then cancel out both pressure terms because there's no difference in the pressure at those 2 points. So let's put a 0 there. The velocity of the water at the surface is 0 because it's moving down very, very slowly, so we can assume that in comparison to the exit, that velocity is pretty much 0. We have a H value, which is the static height, and then we have a pressure head due to pressure, and because we're assuming atmospheric pressure on both sides, that's also 0. We said that atmospheric is 0 pressure. So in terms of the velocity, we have a velocity 2 squared over 2G. That still stands because we don't know what that velocity is. And we have 0 for the height because we're using the exit of the pipe as our reference point. And then we've got the head loss. So the only thing left in this equation is our static height, and then we have the term for the velocity and the term for the head loss. So essentially what we're saying is that the static height, or the potential energy of the water due to its height, is all converted into either velocity, a velocity head, or a head lost in the pipeline. So the next thing we need to look at is the friction loss in the pipeline. So the Darcy-Weisbach equation that's expressed as HF equals F LV squared over D to G. We can now combine these equations. Let's leave it over there. We can substitute our friction loss as the last term of the equation. So we've got H is equal to V2 squared over 2G, 1 plus F L over D. So we're just simplifying, we took V squared over 2G out, and we've got 1 plus, so that is a 1. One plus FL over D. So simplifying in terms of velocity and square rooting, we'll get 2GH over 1 plus FL over D. So we've determined, with those two formulas, we've simplified all our terms to give us a formula in terms of velocity. V2, the exit velocity of the pipe. In terms of the friction factor, the length, the diameter of the pipe, and also the static head. So now, it's a simple matter of substituting those values into this equation. Let's substitute 2 times 9,81, which is our G value. The static height we were given at the beginning is 3 meters. And underneath the lower terms, we've got 1 plus our F value, 0,015. L over D, 6 meter long pipe. The diameter is 0,008. So from there we can calculate our velocity at the exit of the pipe to be 2,192 meters per second. So that was the first thing where we were asked to calculate. The second thing is flow rate, which is determined by the letter Q. So Q is velocity times the area of the flow, or substituting for area, we have pi d squared over 4. So therefore, we can say the velocity, which we just calculated as 2,192 meters per second, times the area, which is pi times 0,008 squared over 4 will give us our discharge of 0.11 liters per second. Alright, so those are the two values that we were asked to calculate. In this problem, we also went along just to check for turbine flow. So this was all based on the fact that we assumed turbulent flow in the pipeline. To check whether it is turbulent flow, we can calculate the Reynolds number using Vd over mu, and the velocity is 2,192 meters per second. The diameter of the pipe is 0,008. And we did look up the kinematic viscosity of the water at the start. That was 1,14 times 10 to the minus 6. So that gives us a value of 15,400. And that is greater than 3,000, therefore turbulent. Flow. And that's the end of this problem.